Okay, so this is today's lesson. Yep. All right, we are going to talk about row space, column space, and null spaces. Right? We are going to talk about these spaces. These are very easy. So let's consider a matrix a matrix m by n. A is a matrix. It has m number of rows. A1, A1, A2, 1, yeah, A M1, yeah, and n number of columns. N number of columns. A1, 2, A1, and something like that. M by n, right? So right. So if you separate this matrix, let's consider only rows, right? So all rows. How many rows are there? There are m number of rows. So how many so if you consider one of rows, let me consider r row of A, right? Which is A R1, the first element. A sub R2 up to how many columns do we have? N columns. All right. How many coordinates do we have? 1, 2, n. 1 to n number of coordinates. Okay, this is an element of Rn, right? Because these are real numbers. Right here we are considering m by n real matrices, right? These are real numbers, so this is an element in Rn. If you write a combination of these rows like this is the first row, this is the second row, this is the mth row. This is the combination of rows of A. This is a linear combination of rows of A. We know that this row, if you consider any particular row, any row, so it is which is a element in Rn. Therefore, this combination, so if you consider this set of all combinations of this row is a subspace of Rn. So subspace of Rn. So Rn. Right. So this is called this subspace. So row space. This is called row space of A. This linear combination of rows of A is called the row space. This row space is a subspace of Rn, vector space I. And if you consider columns, linear combinations of all columns of A. So you know columns. If you consider columns here, so this is a column. Contains 1 to m. This is let's write the first column A 1 1 A 2 1 dot 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 A M1. This is the first column of A. And how many? So let's just notice the uh, this number here, right? This is an element in Rn. Right. If you consider set of all combinations of linear combination of columns of A, that would be a subspace of Rn. You know that. That's a trivial, right? Consider all linear combinations of columns of A, that would be a subspace of Rn. All right. So does that make sense to you? Is it easy for you to understand, or let me give your feedback? Give your feedback. Give your feedback. Let you give you feedback. Is this easy or difficult, or did you understand? So row space is a subspace of Rn, and row space. What do you mean by row space? What do you mean by row space? Set of all linear combinations of rows of A. What do you mean by column space of A? Set of all linear combinations of columns of A, right? So row space is a subspace of Rn. Column space of A is a subspace of Rn. I think this makes sense, right? Right. If you, I think we know this one. This is a homogeneous one. This is a homogeneous one. If you consider all the set of solutions, a set of solutions of this homogeneous. So we give a name for that space. If you consider, we know, we can show that this one also a subspace Y. Let me show that one. I think we showed that. Yeah. So here, look at this. A is an m by n matrix. Then set of all solutions of the homogeneous system is a subspace of R and Y. So here let's this has n number of rows, and this has n number of columns. If you want to define A times x, the dimension of A is m by n, and this is a vector. So if you want to define this, this should, the dimension should agree, right? So and this should be n by 1. Therefore x is an element, the x is an element in R n space if you consider the set of all solutions of this homogeneous system, which is a subspace of Rn. Let's show that you know that trivial solution. If you sub zero 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 n number of zeros. So this vector trivially satisfies this condition. Therefore, 0 is a solution to this linear system, homogeneous system. If you pick two solutions of this homogeneous system, x1 is a solution to this, x2 also a solution to this. You know this. These two satisfy this system, homogeneous system. That is, yep, ax1 is equals 0 vector, ax2 is equal to 0 vector. So we have to show the set of all solutions of this homogeneous system is a subspace, and we know that zero belongs to that set, the set of all solution of this one. That means this set is non-empty, right? Non-empty. If you pick any arbitrary two solutions to this homogeneous system, so we have to show we have to show this one is closed under addition, vector addition, and closed under scalar multiplication. Okay, let's add these two. Then add these two, you get x1 plus x2. So we have to show this one also a solution to this homogeneous system. Let's check that one. Let's multiply that one by A matrix. You can expand this bracket. You get AX1 plus AX2. You know AX is equal to 0 vector. This one also. Therefore x1 plus x2 belongs to this set. That means this set is closed under vector addition. So this is your vector space now, Rn. Rn, vector addition, scalar multiplication over the field R. Right. So closed. So this set is closed under addition. Again, you can show this set is closed under scalar multiplication, right? Therefore, the set of all solutions to this homogeneous system is a subspace of I, right? So this is called null space of A. So null space of A means solutions of solutions to the set of all solutions to this homogeneous system, right? So does this make sense? So note that the null set of A is called the solution space of right? We know that the solution space of this homogeneous system is a subspace of Rn, right? Right? Because X is an element. Here, X is an element in Rn. The solution set is a subspace of I. All right. So, give your feedback. Did you understand this or not? I think you understood. Did you understand, or do you have any questions, or just let me know. All right. So, all right. Then this one is a subspace. The set of solutions to this homogeneous one is a subspace of Rn. Yeah, which is called null space. Here, set of all solutions X in Rn such that all solutions to this homogeneous system X satisfies this equation. So set of all solutions to this homogeneous system, which is called null space. All right, we have three spaces: row space, column space. Row space is a subspace of Rn. Column space is a subspace of Rm, and also null space is a subspace of Rm. Right. This is clear, I think. Right? Don't know. Right? We'll give some exercises to check that. All right. Right. So these are column vectors. Yep. Right. Let's dive into this theorem. So, A is a matrix. Dimension is m by n. Is rho equivalent to the matrix B, the same dimension. Both are. This one is rho equivalent to this matrix. Then the row space of A is equal to row space of B. All right. So if A is row equivalent to, so these two matrices have the same row space, right? So we know that if you consider A, matrix A, so you know that you can do row operations by using row operations. You can obtain another matrix, say B, right? So you know that these two matrices are equivalent, right? So if you consider then the row space of row, so let's denote this one. Wait a second. I will denote the row reduce one. Yep, elementary row. Yep, this one row reduce one is R of A. So here A is given, A is a given matrix. You can perform row operations. You can reduce this matrix to row reduce matrix, right? You know how to do that. So the row space of A is the same with row space of the reduced one, right? The row space of A is the same, both are the same spaces, row space of reduced one. So elementary row operation can change the column space, right? Because you are doing row operations, right? So it will change, but right? So here you have A. So this is your column. These are your columns, right? So if you take the transpose of, consider transpose of A, then what happened to these columns? If you transpose this A, these columns become rows of this matrix transpose of A. Right, then you can reduce this matrix reduce using operation. Then you can find the reduce one, then row operation, then the row space of this is same with the row space of reduce one, right? Then all right, reduce one Then you can again you can transpose this one to obtain. Yeah. This can do many things. Let's take many problems to understand those things, right? But but make sure that every row operation can change column operation. If you want to find column operation, column space, you can do this trick. So when if you have A, these are the columns, and take the transpose of this matrix, then these columns become rows. Then you can do row operations for these things, and then you can find row space of this. Then row space of this one becomes the column space of A. Let's do a couple of examples to understand that, right? Pretty simple, right? Here A, these are columns. If you want to convert this one to the rows, take the transpose. This becomes this line becomes this line, like that. Then do your operation, row operations, and find, you know, that row space of transpose of A is equal to row space of reduce one. Here, reduce one of this, right? Then the row space of this is same with the column space of this. Let's do a couple of things, right? Examples. Okay, so yep. So how about you? Did you get that? Oh no, get that? Oh, this thing is small. I think grade 5 questions, right? Yeah, if you want to change the push this column to be a row, just take the transpose and consider over and so on, right? Grade 5 questions, right? Okay, all right. So basis for the row operation of matrix. All right, let's find a basis for this subspace. Yep, this row space. So if a matrix A is a row equivalent to reduce echelon. Yep. So you can reduce A. You know that. So you know that A. This is A. So you have row space of A or linear combination of rows of A, right? Which is a subspace of, I don't know how, I don't know, we have discussed that. So this space is same with the reduce. If you can reduce this matrix to this, right? So we know that it is not, both are the same. If you perform row operations, the row space is never changed, right? Right? Yeah, row space of A is same with row space of reduce. So if you want to find basis for row space, reduce this to reduce to echelon form, row echelon form. Then the non-zero rows of the echelon form will be a basis for your row space of A. Let's do a couple of examples to understand that. Right, this is your matrix. It has 1, 2, 3, 4, 5, 5 rows, and then columns, 1, 2, 4 columns, 4 columns. Dimension is 5 by 4. All right, so you can reduce this one, right? You know how to do that. So just focus on how do you reduce this. Just focus on the first row. This is the non-zero element. Then this is the pivot element, and then you have to kick off all elements under this pivot element. So this one is all right, 0. You have to kick out this one and kick out, vanish this. You have to vanish this one. You know how to vanish these elements with this, right? And do those things. Then go to the second row. And what is the first non-zero element? This one. Okay, then this is the pivot element in row number 2. And kick out, this is already 0, this is already, kick out this one. You know how to do that, right? And keep doing that, then you can obtain this one here, right? You look at this. This is the pivot element, first non-zero 0. First non-zero element should be equal to 1. When it comes to the second row, the first non-zero leading element is this. When it comes to the third row, first non-zero element is 1. All right, leading. Or there are how many non-zero rows? There are 1, 2, 3 rows. So this is the reduced echelon one, right? Reduced echelon form of A. And if you want to find a basis of row space of A, so you just need to consider the non-zero elements, non-zero rows of the reduced echelon matrix of A. So the base of the row space of A would be generated by these base elements. Right, this one. Yep. The row space of A would be generated by these three non-zero elements. This is the basis element. This is one of basis elements. Another base elements, another one. It can, so this set here, it has how many elements? 1, 2, 3. So the dimension of row space of A is 3. All right. So this is how we find the row space. Base, yep, row space. Rows, bases. If you find bases, so this generates your row space. So these are the base elements. So this, if you consider the spanning set of these one, so you get the row space of A. All right, does that make sense? I think this makes sense, right? So if you look at these columns here, look at these columns. So this one is linear independent. Yeah, this vector, this column cannot be written in terms of, yeah, you cannot write this one in terms of this one. That means these two are linearly independent. But you can write this column in terms of no, you can write, yeah, these three. Look at these three columns. Look at these three columns. So using these three columns, so B3 column can be written in terms of B1 and B2. B1 and B2. That means B1, B2, B3 vectors are linearly dependent. Linearly dependent. This is the relationship here. because because why I am saying it is linearly dependent. If you take this term to other side, then this minus 2b1 becomes positive b1 vector, that column b1, right? And yeah, and let's bring this term to other side, then it becomes negative, and this remains the same, positive b3, which is equal to 0. Oh, this system here, this is, so here this is your C1, C2, C3. So this is non-trivial solution to I think you know, right, to be these are to this system. Therefore this is this b b1 b2 b3 linearly dependent, right? So right, all right, we know that. So b1 b2 b3 is linearly dependent. Then we can say, from that fact we can say A1, A2, A3 also linearly dependent. A1, A2, A3 also linearly dependent. This is the relationship. So, and look at these three. See, look at this. We know these two linearly independent. You cannot write this column in terms of this. But here, look at this one. Look at this. This has this component. You cannot, because there is no component here, both are 0. You cannot write this one in terms of these two. Therefore, B1, B2, and B4 are linearly independent, because here, so in B1 this position is 0, in B2 this position is 0. You cannot get 1 from these two. Here you can, because both are 0, right? Therefore you cannot write B4 in terms of B1 and B2. Therefore, B1, B2, and B4 are linearly independent. Because of that, then you can say B1, A1 column, A2 column, and A4 column are linearly independent. Check that one as well. That is true. All right. Because both matrices are equal. That's the thing. So you can do row operation. When you do row operations, these matrices are equal. That's why, because of equivalence. So A equivalent to B. If you perform row operations, means A and B are equal. Therefore, if you have some properties in B, you can notice those properties in matrix B, A also. So because B1, B2, B3 independent, linearly independent, and we can then we can say A1, A2, A4 also linearly independent, right? Okay. All right. What is this? All right. There's another example. Find a basis. You can go through this. What else? Find a basis for column space. All right. Let's find a basis for column space. So I think you remember our grade 5 approach. Yep. Yep. So if you want to find column space, because when you do row operations, the column space here, you remember, right? Element row operations can change the row column space, but if you transpose this one and do row operation to this, you know that this is equivalent to this reduced one. Then row operation of this one, same with row operation of this. Then you can consider the transpose of this one again. Then that will be the basis. All right. All right. What is yes that? Yeah, this one. Find a basis for column space of this matrix. All right. Transpose this. This becomes this here. This becomes this. Yep. Yep. This becomes yep. Yep. This becomes this. Yep. Transpose and reduce this. Perform row operation. Da, 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 da. You get this. These non-zero rows are the bases, are the base elements of row space of A transpose. Right. Therefore, these are the base elements. Therefore, these are the base elements of column space. Right. Yep. Column space is equal to row space of column space of A is equal to row space of transpose of A. So the base of a column space would be the base of a row space of A transpose. This one. All right. This would be the basis. This would be a basis for column space. You can find infinitely many bases. Infinitely many bases. Yeah. But here note that here this base is not a subspace of column 1, column 2, column 2, 3, column 4. Why? So when you do row operation, this is not a subspace, not subset of C1 and C2. So if you find a subset of C1, C2, C3, and C4, so what would you do? So you take this A and do row operations. Reduce this one. Reduce this. All right. Now you are going to find a subspace of C1, C2, C4. These are C1, C column 2, column 3, column 4. So reduce this, reduce to this, right? Now look at this, analyze this reduced one, because this is very complicated. Here there are a lot of numbers. If you reduce this one to this one, right? So very easy to analyze here. This cannot be written in terms of this. These two are linearly independent. But look at this. Yep, this is non-zero. Both are zero. Then these three vectors are linearly independent. Therefore, you can say, yep, this one. Then column 4 and column 1 and 3, 1 and 2 are linearly independent, right? Yeah, this is a base, another basis for column space of A. This is another base of another basis for column space of A. But this one, this basis, this basis V1, V2, V4 is this base is a subset of, yeah, this base is a subset of C1, C2, C3, these columns. But previous one is not a subset of these columns. That's the difference. You can choose any way, any method, right? You can transpose this and reduce that one, then you can find a basis, or in this way you can find a basis, right? Anything is fine, right? But if you want to find a yeah, if you if you want to find a basis which is a subset of these all columns, don't transpose this, just reduce this one itself, right? Just reduce this one itself to the echelon form, then analyze this matrix. Yep, these two. Yep. So you cannot write V4 in terms of V3 and V1, or V2 or V1. Therefore V1, V2, or therefore V1, V2, V4 in linearly. You can find another one. V1, V3, V4 also linearly independent. Therefore C1, C3, C1, no, C4, C3, C1 is linearly independent. You can do like that. You can analyze like that, right? So I hope this makes sense. Let me stop recording. So gradually number of participants is reducing. I don't know why. I